Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be doing another problem on how to calculate the change in free energy for a reaction. And again, I'm going to use the equation of calculating the standard free energy from the standard enthalpies of reactions, of standard enthalpy of formation, and also the standard entropy changes. So again, the equation I'm going to be using is delta G, standard free energy of a reaction, is equal to the standard enthalpy change of a reaction minus the standard entropy change of a reaction multiplied by the temperature. So the temperature we're given is standard temperature, 25 degrees Celsius, but we're going to add 273 to that to get 298 Kelvin. So remember, temperature has to be in Kelvin because the units are in Kelvin, especially for the entropy change. So that's joules per Kelvin. Okay. So then all we need to do is calculate the delta H formation of a reaction. I'm sorry, the standard enthalpy of a reaction, the standard enthalpy change of a reaction, and the standard entropy change of a reaction. And so to calculate the standard enthalpy change of a reaction, we're going to use this equation. So let me fix that. So we know that the standard enthalpy change of a reaction is equal to the sum of the heats of formation of the products multiplied by their coefficients. So N is the number of moles from the coefficient. So the number of moles multiplied by the standard heats of formation of the products. So it's going to be products minus reactants. So if I said reactants, that was a mistake. It's products. So products minus then the sum of the reactants. So it's going to be the moles of the reactants from the coefficients multiplied by the change in the standard heat of formation of those reactants. And so this is our equation. So over here we have the tabulated information we need. We have our standard entropies. We have our standard heats of formation of NO, oxygen, and NO2, which are in our balanced equation here. So we're going to go ahead and fill everything in. So this is going to be equal to, now products, we only have one product. The coefficient is 1, so we're going to put a 1 there, and we're going to multiply that by its enthalpy of formation, a standard enthalpy of formation. And so this is NO2. So NO2 has a delta H for a standard heat of formation of 33.2, and that's kilojoules. So 33.2 kilojoules per mole. And here we're multiplying by moles, so moles are going to cancel out. And that's our only product. So now we can subtract out the sum of the reactants. We have two reactants. So let me put square brackets here. The first reactant is NO. We only have one of those. So that's going to be 1 for our N, right? Our N here. And we're going to multiply by the delta H of formation, the standard enthalpy of formation. And that is right here. So we got 91.3. So 91.3, and again, that's kilojoules per mole. And then we're going to add to that, because we're summing this together, which means adding, we're going to add to that the oxygen. So our coefficient for the oxygen is 1/2. And for oxygen, the enthalpy of formation, the standard enthalpy of formation is 0. Elements in their standard states have an enthalpy change of formation of 0. So that's going to be 0. Close that with the square bracket. And so now I have everything filled in. Now all I have to do is just calculate. And when I do, I get, what did I get for that? And what I get here is a negative, what did I get? 58.1 kilojoules. And of course, we're going to have to convert this to joules because we're going to put it into this equation. And when we have our standard entropy change of a reaction, that's going to be in joules per Kelvin. So we want this to be in joules as well. And so we'll just use our conversion factor. So we know that 1,000 joules is equal to 1 kilojoule. We'll put 1 kilojoule on the bottom to cancel out here, and 1,000 joules on top. So kilojoules cancels out, and we end up with negative, can't forget the negative, negative 5.81 times 10 to the 4th joules. So this is our standard enthalpy change of a reaction. All right, next is finding our standard entropy of a reaction. So the change in the standard entropy of a reaction is basically identical equation. The only difference is instead of delta H's, we have standard entropies that we are going to be using. So the standard entropy of a reaction is equal to the sum of the products minus the reactants. So it's going to be, in this case, we're going to use standard entropies of products minus the sum of the standard entropy of reactants. So again, using our tabulated information here, we're going to use our equation. So products first. So we have 1 here. So 1 times the entropy of NO2, which is 240.1. So 240.1. And that's, again, joules per mole Kelvin. Joules per mole Kelvin. And then that's our only product. So now we're going to subtract out reactants. And so our first reactant is NO. We have 1 of those. So we're going to put a square bracket here since we have 2 or more. So 1 of the NOs, and then the standard entropy of NO is 210.8. So 210.8 joules per mole Kelvin. And then we're going to add to that oxygen, the second reactant. So oxygen here is 205.2. And we have 1/2. So we're going to take 1/2 and we're going to multiply that by 205.2, 205.2, and again, that's joules per mole Kelvin. And we're going to close that with the square bracket there. And so again, we are going to do the calculation, and we'll calculate what our standard entropy change of a reaction is. So what did I get? And I got negative 73.3. So that's equal to a negative 73.3 joules per Kelvin. So this is my standard change in entropy for the reaction. So I've got my entropy change, my enthalpy change, Now I can plug those along with the temperature into that equation. So therefore, delta G, the standard entropy of a reaction, the standard change in entropy of a reaction is equal to the standard enthalpy change of a reaction, which is negative 5.81 times 10 to the fourth joules minus, and then we're going to take the standard entropy change of a reaction. That's negative 73.3 joules per Kelvin. And we're going to multiply that by the temperature in Kelvin, 298 Kelvin. So Kelvin cancels out. So I have joules left. I'm subtracting joules from joules, or in this case, adding, because a negative times a negative is a positive. So I'm adding a positive to a negative. So let's see what this gets us. And so we get a negative 3.63 times 10 to the negative, to the fourth power in joules. Let me double check that, 3.63, yes. So this is the standard free energy change of this reaction at that temperature under standard temperature. So that means that since it's negative, this reaction is simultaneous under standard temperature. So I hope this was helpful. If you enjoyed this video, if you learned something from this video, if you like this video, then please like the video. Hit that like button over there and also share it with your friends. Make sure you subscribe to my channel. Hit that notification bell so you can be notified by all the videos I put out, and that means that you should click the all button. And then finally, put a comment down below. Ask me a question. Tell me what you think. I'd love to hear from you. Thanks for joining me, and have a great day.